Hi everyone, welcome to the talk on Wigner's applicability problem. It is my pleasure and honor to be invited at the Topos Institute for many reasons, including Valeria, who invited me to this talk, is the person that originally inspired me to work on Wigner's problem. So I'm very grateful for that. Also, I think all the mistakes that I make are she's responsible as well. I'm kidding.
Yes.
So this
Thank
is
you,
a
Arezoo. Yeah, we're very honored to have you here as well. Yeah,
thank you very
please,
much.
please continue.
Thank you. So I'm going to be talking about applicability of mathematics, but I'm going to frame it in a particular historical moment. A talk was given by Eugene Wigner in 1959, when later he published it in 1960, which probably a lot of you recognize the title as the Unreasonable Effectiveness of Mathematics in the Natural Sciences. So I'm going to frame the applicability problem as the problem that Eugene Wigner reformulated, and then we look at how we can think about it in the contemporary landscape. So Wigner is responsible for introducing this very dramatic phrasing of the unreasonable effectiveness of mathematics in the natural sciences. As probably a lot of you know, he got the Nobel Prize in 1963 for his contributions to the theory of atomic nucleus and elementary particles through the discovery of fundamental symmetry principles. So he was responsible for bringing group theory into physics. So what is Wigner's applicability problem? So the applicability problem is the problem of explaining why mathematics plays the fundamental role that it does in natural empirical sciences. So I want to highlight a couple of things. It's a question of why. So you have this kind of intimate relationship between two fields of human knowledge or several fields and mathematics. And the question is that why is that does relationship exist? Wigner calls it the empirical law of epistemology, which I would talk to you later about why is it called empirical, why is it a law of epistemology as opposed to a law of metaphysics. And the way he introduces it is he calls it the appropriateness and accuracy of the mathematical formulation of the laws of nature in terms of concepts chosen for their manipulability. I'm very puzzled by this particular problem because whenever I introduce it, even, I'm sitting in a cafe, people say, oh, what do you work on? And I talk about applicability problem. The reactions are really interesting. For some people, uh, it's completely like it's a miracle. We don't know. It's like there's something really mysterious, Wigner talks about it like that too. They're like, God has created things such that they fit together. And then for some people, they're like, what are you talking about? Obviously, math would be applicable in other areas. So the range of responses, it goes from the kind of extremely like mysterious to extremely trivial. And I have always puzzled over why do we have such a range of reactions. So I'm just going to make a footnote about the applicability problem is more than a historical footnote, more than a historical curiosity for us. It's not just kind of a scholarship about, oh, somebody in 1960 says something and then we are still musing over it. But use of mathematics in different branches of human knowledge has not become less. If anything, it has become much more. So in theoretical physics, we have the role of abstract mathematics is ever more prominent in AI, in data science, in other fields, in economics, in medicine, in biology. So mathematics continues to play the fundamental role it has been playing maybe historically in physics in more branches of I can call them empirical sciences. So I'm not going to go over this, but just to tell you that the applicability problem is a very relevant problem today as well. Okay, so why would there be a problem, you know? Okay, yeah, math is, some people say it's a language, some people say it's a tool of cognition, some people say, well, like, you know, so what is so puzzling? I want to walk you through motivating Wigner's applicability problem. Why does he think there is such a major problem? So first of all, we got to ask ourselves, what is mathematics? Which I'm going to ask all of you guys at the end as mathematicians. But when Wigner responds to that, he says mathematics is the science of skillful operations with concepts and rules invented just for this purpose. Okay. The emphasis for him, as we go on and see, is about the beauty and about manipulability of mathematical concepts. So it is in this space that we bring Hardy's, a mathematician's apology. He says, the mathematician's patterns, like the painters or the poets, must be beautiful. The ideas, like the colors or the words, must fit together in a harmonious way. Beauty is the first test. There is no permanent place in the world for ugly mathematics. We love that quote. Then I brought you something from Russell, which he says mathematics possesses not only truth, but supreme beauty, like that of a sculpture, without the appeal to any part of our weaker nature, without the gorgeous trappings of painting or music, yet sublimely pure. So hold on to the term pure, and capable of a stern perfection such as only the greatest art can show. The true spirit of delight, the exaltation, the sense of being more than man, which is the touchstone of the highest excellence, is to be found in mathematics as surely as in poetry. Okay, so mathematics is understood in this view as more of an artistic creation, so you can call that maybe the static view of mathematics. Later, we realize this is a more philosophically understood, it's a formalist view of mathematics. So mathematics, on one hand, is this free creation, as Cantor also put it, free creation of the mind. Sometimes we say mathematicians sit in their windowless offices and they come up with these like fascinating structures and patterns that end up being so applicable in other areas. So how is that possible? That so that's mathematics for Wigner. Then he defines what is physics. Okay, so he says the physicist, now the mathematician is in the sky, the physicist, unlike the mathematician, is interested in inanimate nature, so now he's looking around, and in discovering regularities that exist among the natural phenomena. So physical objects are said to be causal and spatiotemporal, while mathematical objects, on the other hand, stand outside the flow of time and causality. Now, this is not necessarily a distinction that I will endorse, but I'm walking you through why for Wigner there is this pressing problem. So as we saw it in first glance, and I'm very happy to delve in it deeper in Q&A if you want, it seems that the puzzle comes from a situation that there is a distinctness between mathematics on one hand and physics on the other. And the distinctness is such that there is a puzzle about why there seems to be such a good fit, given that by his definition, mathematics is not developed, or by maybe many people's definition, with an attention to laws of nature, with an attention to how our like empirical world works. So Wigner has this kind of funny, puzzling quote. He says, our situation in this case is like a man who was provided with a bunch of keys and who, having to open several doors in succession, always hit on the right key on the first or second try. So the image is of a mathematician or an artist who creates these beautiful mathematical concepts, call them keys, but they are just have been created to be put in a beautiful exhibition. And now all of a sudden you're given those keys and go and try to open doors in succession, which is like find or formulate regularities in the natural phenomena, and you keep getting lucky. So it's not that one law of nature is written mathematically, but according to him, all laws of nature in physics or all regularities are written with the language of mathematics. So it's not only him that Wigner puzzles over this. I brought you a couple of quotes from Dirac and Hilbert around the same time. So Dirac says, a mathematician plays a game in which he himself invents the rules, while the physicist plays a game in which the rules are provided by nature, but as the time goes on, it becomes increasingly evident that the rules which the mathematician finds interesting are the same as those which nature has chosen. So you see, Wigner is talking about the fit of mathematics and physics. Now, Dirac takes it a step further. He talks about the fit of mathematics and nature. So that's like another step, which is nature seems to be playing the same role. I also brought you a quote from Hilbert, which he also uses the term a miracle. So the miracle of the harmony between being and thinking. So being as that which exists in the world and thinking that we have. So the harmony of the mind and body, another way to put it. Okay, so what we had so far is I defined what is mathematics from Wigner's point of view, what is physics from his point of view. Now he says, what is the applicability problem? And the terms that are interesting to me are like the terms that he uses as a miracle and as a mystery. So like, why is it that for somebody who brought group theory to quantum mechanics, like why would that be so puzzling? I mean, I puzzle over that puzzlement. So he says the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. Okay. We should be grateful for it and hope that it will remain valid in future research and it will extend for better or worse to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. Then he also talks about the enormous usefulness of mathematics is something bordering on the mysterious and there is no rational explanation for it. So why am I bringing these quotes from him is to tell you that Wigner seems to be thinking that the relationship between mathematics and physics is something of a mystery for which we cannot find any rational explanation. And among the normal people, when I talk with them, some people still seem to be thinking that, but some people think there's absolutely nothing to puzzle over. Similar with when I talk with our colleagues in math departments or physics or philosophy. So I'm curious later to know what you are thinking. Okay. So here seems to be Mark Steiner in 1998. He summarized the argument. This is a reconstruction. Seems to be the first premise is mathematical concepts seems to arise from the aesthetic impulse in humans. It is unreasonable to expect that what arises from the aesthetic impulse in humans should be significantly effective in physics, because physics is the study of empirical nature. Nevertheless, a significant number of these concepts are significantly effective in physics, hence mathematical concepts are unreasonably effective. So that seems to be more or less how this Wigner paper is being read. Okay. So there is no shortage of responses to the Wigner's applicability problem, but I just brought you for fun some of the titles. So some people talk about the unreasonable ineffectiveness of mathematics. Some people talk about the reasonable ineffectiveness of mathematics. Some people talk about the reasonable effectiveness of mathematics. So all varieties of how this could be read by different people. So some people go and say, look, math is not that effective in other sciences. Like, what are you talking about? I mean, look at the efforts that have been done in sciences, maybe other than theoretical physics. Well, things are not really that effective. Like, math is not that effective. Also, you might say, even when math is effective in physics, it's not the pure math, it's not the rigorous math that mathematicians are interested in. So when I was at Stanford, people were teaching a class on Hilbert spaces, but what they taught on Hilbert spaces in math department and what they taught on Hilbert spaces in physics, they're different from each other. So you might say, it's not that math that is useful. You also might say, well, it's not true that mathematics plays a major role in physics, because physics before 17th century, before 18th century was really not that mathematical. Look at Aristotelian physics, look at like physics of substances. So not only is that mathematics is not effective in all empirical sciences, but also in physics, you got to be careful what you're talking about. Some people will say, rightly, that not all of math is useful. I mean, we would like to maybe say these kind of things when maybe we want to get grants, but usually, like, it's not true that all of math is useful or it will become useful one day in empirical sciences. Now, I want to think with you about the use of math in math itself. And also, another thing is that you might say, well, that something is formulated mathematically is not a test for its truth. We've had many theories of physics written in the language of mathematics. They ended up being false. So what's the, what's all of the hype about? I'm sure you guys can add to this list of, but these are normal reactions. People say, okay. So I want to tell you that, so this is part of my PhD work and then my later research. I want to tell you that these reactions seem to have kind of not understood Wigner's work. So I'm going to walk you through a little bit of more historical and nuanced work of what do we have here. It's not, because it would be very puzzling to me that a physicist like Wigner would make such, big mistakes as something that everybody would notice, but he hadn't noticed that obviously not all of math is useful. Like, that sounds. So for the rest of the talk, I'm going to talk with you about, to a large extent, Wigner does acknowledge these limitations. So why is it that the puzzle still remains? And then I'm going to walk you through what is it that is interesting in this problem for us. Good, continue. Okay, great. So remember, I said, okay, the reactions to Wigner want to make the problem much smaller in a way and more delicate than what it looks like at first sight. So it's not so much, people say, applicability of mathematics to all natural sciences, but it's to certain areas. Well, I think while the title of Wigner's paper is misleading, he actually also only discusses modern physics. Now, in order for you to be convinced on that, you gotta, if you can, you gotta read a bunch of my papers that I look at exactly like, yeah, I mean, the title is misleading, but the rest of the paper and the rest of the body of his philosophical work focuses on modern physics. So Wigner's question is actually is not the question that sounds at the beginning, but it's something like that. He says, what is it about modern physics that has made it possible for mathematical concepts to play such a fundamental role? So you see, like you almost, sometimes I think about it, imagine like you have two people from completely different origins, like let's say for an example, like a woman and a man, that one of them comes from like royalty and the other one comes from a different socioeconomic place, and then they come from different countries, and all of a sudden they have this like 300-year-old marriage that is lasting and is great. And so you got to ask yourself, first of all, like, what is it about them, each relata of this relationship, that have made this relationship possible? But sometimes we wonder about what is it about mathematics that has, has made this fit possible. But it seems Wigner's question is, what is it about physics that makes it possible for mathematical concepts to play such a fundamental role? This is going to help us because then we can ask ourselves, do other sciences have this particular structure? How can we move forward? So the answer that he gives, he says, look, physics seems to have, modern physics have a peculiar structure. He calls it like the structure is kind of a three-level structure of initial conditions, laws of nature, and invariance principles. Okay. So I'm going to talk to you a little bit about that. So he seems to be suggesting that the objective of physics at some point kind of changed. Instead of wanting to explain the nature and everything we find, the objective has become to explain regularities in the behavior of the object. So the scope of physicists' objective is therefore restricted to domains in which these regularities can be found. So according to Wigner, the greatest success of physics is due to this restriction in its objective. So what does that mean? It means that there is this kind of a decision, there is this kind of a structure that says, okay, there are domains in which I cannot find regularities, fine. There are places I can find the regularities, and the regularities can be formulated mathematically, and there are these regularities, in order to be formulated mathematically, they need to have a certain structure. I'm going to walk you through that. So he says, we have devised an artifice that this is like for him with the rise of modern theoretical physics, which permits the complicated nature of the world to be blamed on something that is called accidental. And thus, so you can say, okay, what are the constants in nature? Why do they have the value they have? Well, we don't know, but we can tell you, if you give me the certain constants, I can tell you about the relationship of certain parameters with each other. So it allows us to abstract the domain in which simple laws can be found. The complications are called initial conditions, the domain of regularities, laws of nature. So he says, unnatural as this division of the world structure may appear from a detached point of view, and probable though that the possibility of such a division has its own limits, the underlying abstraction is probably one of the most fruitful ones that human mind has made. Okay. So I'm not going to read all of this, but he says there is a structure of modern physics, which is basically what science, what physics wants to uncover are certain correlations between the events. And what we have realized is that these correlations between the events have a certain structure, which he calls them the laws of invariance. That, what does that mean? It means that you can safely assume if you do a certain experiment in a particular time and a particular location, keeping the initial conditions fixed, you can repeat the experiment elsewhere. So there is kind of an invariance in relation to displacements in time and space. And then we have other symmetry principles as well. So these symmetry principles, so he says, indeed, classical physics teaches us that the size of a planetary orbit is not the sort of thing we could aspire to predict. So there is a sharp distinction between basic laws, which govern the evolution of systems in time, and initial conditions, which must be put by hand in. So it is the distinction, it is the separation of these fields that has allowed us to create these equations or to create these relationships among the events. Or so the idea is that the nature is such that, and this is a contingent fact about our world, that certain regularities exist, but because we have discovered that these regularities have certain invariance principles that they govern them, we have formulated them mathematically. Okay. So Weinberg says in modern quantum mechanics, as well as in Newtonian mechanics, there is a clear separation between conditions that tell us the initial state of a system and the laws that they govern its subsequent evolution. So what are we learning so far? We are learning that it's not that it's not that the entire inanimate nature, according to physics, is mathematical, but it is that the laws of nature are written mathematically. And why is that the case? Because of this understanding of, let's not bother with the initial conditions, because in principle, you can think the entire universe has to be taken into account to discover any irregularities. But the fact that we've made this artificial distinction has allowed us more or less to abstract the realms in which regularities can be found. And because those regularities have these invariant structures, they can be formulated mathematically. We can go into that more in Q&A. So that's one. So it's not only he says the applicability of mathematics is about modern theoretical physics, but he says it's just only in a particular realm. All right. So I continue. To what extent does he acknowledge these limitations? Remember, I said, well, people say, look, theories can be written in the language of mathematics in all kinds of sciences, and we end up realizing they are false. What's the big deal about it? Wigner also acknowledges that. He gives a few examples of Bohr's early theory of atom, Ptolemy's epicycles, free electron theory, etc. In all of these cases, they were amazing numerical agreements between the theory and experiment, and were formulated in the language of mathematics, but later we realized that these theories are false. So it's not that mathematics is the test of truth. Okay. Third, to what extent does he acknowledge these limitations? He's like, okay, all right. It's not, he also acknowledges that it is not all of mathematics that is useful. So he says, it is true, of course, that physics chooses certain mathematical concepts, and surely only a fraction of all mathematical concepts is used in physics. It is true also that the concepts which were chosen were not selected arbitrarily from a list of mathematical terms. but were developed. And now a lot of people, that's their response. They say, well, actually a lot of concepts we use in sciences are not developed by mathematicians. We develop them ourselves. They are mathematical concepts, but physicists develop them, or economists or biologists. We have a long list, but they say, well, but were developed in many, if not most cases, independently by the physicists and recognized then as having been conceived before by the mathematician, like matrices, like, maybe Hilbert spaces, like a version of maybe like complex numbers. Okay, so he accepts all these limitations. So you see, now we limited the problem. So if somebody has accepted all these limitations, why is it that he still says it's such a mysterious relationship, right? Because for a lot of people, once they talk about these limitations, they say, sounds like there is no problem left. Okay. So summary so far, we learned that, first of all, if we are talking about Wigner's applicability problem, we are talking about a limited problem. It is limited to modern theoretical physics. So I want to tell my colleagues who write about the ineffectiveness of mathematics in economics is a really good problem, but this is not Wigner's problem. For the record. He also teaches us, actually, I really like that he asks the how question before the why question. He says, how is mathematics used in physics? So that by realizing, okay, I will look at this later. Sorry, thought the chat is a direct message. Okay, so, all right, so he asked the how question before the why question. So it's like, if we pay attention to the structure of modern physics, we learn something about, okay, what is it that in modern theoretical physics, what are the philosophical assumptions, if you like, that we have there that have allowed the possibility of this relationship? Also, another thing is that we also need to consider mathematization before application. Now, these are terms of phenomenology, but what that means, it means a lot of the concepts that we talk about in physics are not necessarily things that we get from the nature, that they are themselves idealized. Like we talk about point-like masses, we talk about frictionless surfaces, we talk about, so we don't have these also in our surrounding, but they are themselves idealized versions of what we experience. So also it's not so much that you can jump from the applicability of math in physics to the applicability of math in nature. So let's remember that also. Okay, all about physics so far, and I'm kind of advocated that Wigner is not as a kind of like absent-minded as some people want to make it. Okay, so we have a real interesting problem here. So now how about mathematics? So we talked about physics. When we get to mathematics, Wigner's views are a result of a historical moment he's in, and I think this is an important thing to note. So while he's sophisticated about physics, about mathematics, he adopts uncritically what we call a Hilbert school, like formalism of Hilbert school, in which mathematics is this free creation of the mind. These are like meaningless symbols that they have certain relationships with each other. We can go into formalism of Hilbert and Hilbert school, but I think there is an asymmetry between his sophistication when it gets to physics and when he arrives at mathematics. He's just like, yeah, math seems to be a form of art and aesthetic, endeavor that it comes from out of basically it just comes from our minds. And then, so it is I agree with Unger and Smolin that it seems it's not Wigner's philosophy of physics, but Wigner's philosophy of mathematics that creates miracles out of thin air. I mean, it sounds like this view of math as a formal discipline with meaningless symbols, that's not a view that can be supported in light of many considerations with mathematics. I will walk you through that. Also, Wigner doesn't pay enough attention to the fact that the origin of many of the mathematical concepts is in the empirical world that is surrounds us. But it's fascinating that so you and I, we can like look at the edges of this, wall that I'm standing, like that is behind me. But when we want to talk about a line segment in mathematics, now the line segment there is not, it's kind of, it has no thickness. Or if we talk about line, it extends to infinity and it has like infinitely many points, etc. So when we take things from our surrounding world and we study them in mathematics, something really interesting happens, which is it makes them such that they no longer exist in our surrounding world. So we create idealized objects. So sometimes I think about it this way, that the question of whether mathematics is an invention or discovery, it's probably, it is and definitely has an invention on top of a discovery. Like it's not, we take things from our surrounding world, like geometry, empirical geometry that was for the division of lands. When we study axiomatic geometry, we no longer are talking about, edges of properties. We are talking about something that is a uniquely universal and kind of like idealized concept. We can talk about that too. So what I'm telling you here is that it sounds like the Achilles heel of, and where Wigner went to say, oh, it is mystery, I cannot explain it, is because his view of mathematics was not a defensible view. Now, I want to tell you that to me, in the contemporary philosophy of mathematics, nobody's view is defensible either. So that's where maybe a collaboration between mathematicians and philosophers is much needed. And let me tell you something, that it seems after Thomas Kuhn wrote the book of The Structure of Scientific Revolutions, philosophy of science, from its more kind of like general nature, it went into philosophy of quantum mechanics, philosophy of relativity, philosophy of, so separate fields realized that there are philosophical questions that are unique to these areas. Sadly, such thing has not happened with mathematics, because somehow it seems people, by virtue of knowing arithmetic and algebra and calculus, they think that they know what all of mathematics is. And to me, so this is like now my speculations from here on, it seems what happens, like the mistake that Wigner made, which he comes up with a view of what he thinks mathematics is, and then he tries to explain the fit between math and physics, which he gets in trouble. It seems like, to me, we are putting the cart before the horse, namely the evolving relationship between mathematics and physics, and the evolving relationship between mathematics and other areas cannot be something we explain after we have made our philosophical decision about what math is or what physics is. It's something that has to be among the desiderata. Like this is something that it's a condition for any philosophy of math you come up with, has to take, according to my view, the evolving relationship between math and other sciences as its starting point. Also, it's not a one-way street that mathematics is applicable in other sciences, but also there's the other way around, that the other sciences have kind of affected mathematics, which we need to study if we are to come up with a view of what is mathematics. There is a paper by Freeman Dyson that I like this quote. He says, "I'm acutely aware of the fact that the marriage between mathematics and physics, which was so enormously fruitful, has ended in divorce." And as some of us know, the divorce was kind of like there are many marriages that have been made since 1972. So that's one. The second is that I think if we are to come up with a defensible, sensible philosophy of mathematics, which again, I think there is a big shortage and lack of it in philosophy of math, it has to also take some of the attempts that Wigner did in relationship. Was like, it's like, what is it about physics? What is it about the certain abstractions that we make in physics that have this good fit between math and physics? We also have to look at why isn't it the case that biology or economics or other psychology are as amenable to more sophisticated mathematics as physics has been? Like, what is it about these objects that we want to study? What is it about the phenomena in biology, in psychology, that doesn't seem to be, as easily mathematized? What do we make? What are the assumptions that we need to make in order to maybe see something similar to physics, or even is that good to mathematize everything? Also, such philosophy of mathematics needs to, according to my speculations, need to encourage attempts to create mathematical systems that fit better with phenomena in other sciences. So the intimate relationship between, like, think about mathematics since calculus to this day, the intimate relationship that it has had maybe with theoretical physics has kind of pushed us to work on mathematics, or like certain fields of mathematics. Maybe we need to be rethinking of like what kind of a mathematics we need to be talking about ecosystems, like multi-scale systems and so on. So that's all the talk about the fluidity of math. Also, I propose that a defensible philosophy of mathematics needs to take into account a bunch of different things. One of them is that mathematics has changed throughout the history, but the change is not trivial. Namely, when people think of the mathematics of like early 20th century, which people call it pure math, pure abstract math, of which I can talk to you about, like why it was called pure, like what are the kind of socio-historical reasons at that moment. But to think that the nature of math also has not changed, that we can basically, people were doing rigorous pure math anyhow since the Greeks at least, which it's a view of a lot of people. It's just to me the ignorance about what has happened meanwhile, and all the attempts that have been made, the historical changes in math and its in nature. So whatever philosophy we develop, similar to the fact that we look at the revolutions in physics, or we look at revolutions in other sciences, has to take that into account. Also has to take into account the cognitive roots of mathematics. So both cognitive and historical roots. Also, this is like one of my dreams, to see people working on the applicability of mathematics to mathematics itself. Why is it that we have certain fields in math that seems to be like, you have algebraic geometry, you have, for you guys, we have category theory, we have this, we have that. Like, what is it about mathematics that it applies to other fields within math, like certain fields? Like, what can we learn about this interconnectedness of different areas of mathematics itself by studying that? And as I mentioned, it also has to speak with caution about pure mathematics because that's a long story. But when you look in several centuries leading to us, you realize there was not a sharp distinction between, okay, so this is a mathematician, this is a philosopher, this is a scientist, and this is pure, this is applied, this is speculative. Like people knew all different fields and they were collaborating with each other fundamentally. Okay, so this is an advertisement for me, but that is the end of the talk. I have 4 minutes left. Thank you so much.
Thank you, Arezoo. Thank you so much. Yeah.
So
No,
stop sharing.
yes. Yeah, that was very thought-provoking. Many things, many questions I'm sure the audience has about this. And so now we enter the question section of our colloquium. Let me just remind everyone how this happens. You can either raise your hand and I'll call on you to unmute yourself and ask your question, or you can type your question in the meeting chat and I'll be very happy to ask on your behalf. So I see that we have 2 hands up. David, would you like to unmute yourself?
Yeah, thanks. That was really great. I love that talk. In Steiner's number 2, it seemed like he was, I think you were kind of saying this too, that he kind of assumes no origins to our aesthetics, or like his account of Wigner is saying, like, where did our aesthetics come from? They're just magical, as opposed to we evolved through billions of years of history and like had to find regularities in our phenomenology, and that as we did this, we got better, that we cared about certain things and not others. And so I wondered if you thought of what you thought of this kind of, it seems like almost a Stokes theorem of like, if you know Stokes theorem, it's like what happens inside something, inside of us versus what happens on our surface. And I had this thought of like math as attractors in our epistemology, or like attractors in the way that we are able to know things. These are attractive because they're so beautiful and simple. They attract our attention. We can remind ourselves, we can work with them. And then on the outside, there's this regularity in what's hitting our senses, these regularities in phenomena, and that's science. And because we're embedded in the world, it's our job to kind of let what hits our surface be integrated into what's within us. And so that was kind of the thought that your talk made me have. I was wondering your thoughts on it.
Yes, thank you, David. Wonderful question. So what I hear is that, so like the first part, when you're talking about aesthetics, it is true that mathematics has, like for some of us that we do it, like it's just so beautiful. It's like more beautiful than any art sometimes imaginable. But we still, it seems to me that Wigner's problem is an invitation to ask ourselves, what kind of an art is it, right? Because it is true that like when we hear like a beautiful like sound of, when we hear music or we look at visual arts, etc., there's an aesthetic sense involved, but you obviously don't expect that anything that is being created by our aesthetic impulse or has some also usefulness. So the question is that what happens that something like this form of art plays a role that it does, whereas the other forms of art seem to remain, if you like, in the museums or so. I mean, maybe like the closest to mathematics is music. Like it's a sense of, it has a universality. It has like it. I mean, I don't know. I would be interested in thinking about what is the closest form of art to mathematics. But I agree with you that when we want to tell a story about like why it is that what appeals to us is also has something to do with the nature around us, we got to talk about like also our relationship, our embeddedness in the nature. And you're also right, like maybe if it wasn't the case that the nature was so regular, we wouldn't have been here to be sitting here and thinking about, you know. So the fact that there are regularities in nature, correct, but then the question Wigner is asking is that what has made us be able to formulate these regularities using the language of mathematics that we have, which is, I think then we need to go in kind of more nuanced answers.
Yeah, I think that's one of the most important questions in the world. So yeah, I thanks for pointing it out.
Thank you.
Thanks, David. Thanks, Arezoo. Before I call on more people to unmute themselves, I want to just read to the comments from the meeting chat. So Paul Taylor, he made a comment. Epicycles are essentially Fourier transforms, and they were correct. In other words, in agreement with observations, but they did not predict anything beyond the data, nor did they explain anything. I think this is in response to one of your slides where you talk about epicycles. And another comment from Andre Rodin. So Longo and Monteville's title, reasonable ineffectiveness of maths in biology, is a paraphrase of I.M. Gelfand's talk of the title Unreasonable Ineffectiveness of Math in Biology. So that's very interesting. I did not know that. So now perhaps I'll call on a few people to unmute themselves. Andreas, would you like to ask your question?
Okay. I'd like to make a comment about something that seemed rather strange to me, because some years ago, I was asked to write a definition of what mathematics is. And that definition began with the sentence, mathematics is the study of abstract patterns, which looks an awful lot like what was going on in the physics part of your description of what Wigner does. Well, he doesn't say pattern, he says regularity, but that I think was essentially the same thing. But if one views mathematics in that generality, just studying patterns in some abstract context, then I think Wigner's question can be reformulated as, why does nature, or more specifically, why does physics have patterns for us to discuss? And that, of course, is a very philosophical and maybe theological question. But I think the fit between mathematics and physics is fairly clear once one has the idea that, yes, there are patterns in physics, and maybe a little more. There are patterns which can be understood by humans. Once that happens, mathematics is in a position to connect with it.
Yeah, thank you. Thank you for the comment. So I have some questions for you, but let me say something along this line. So when you say it has a theological feel to it, I think a lot of people have gone that route, including Mark Steiner, that I brought some quote, is that but in this talk, I wanted to separate two things from each other, like the fact that there are patterns, there are regularities, and that we have been able to formulate these regularities using mathematics, you see. So Wigner also talks about that. He's like, well, yeah, I can't tell you why nature seems to have the regularities it does. So maybe that's what you meant by this ultimately is a contingent fact and it is given to us. But the question of applicability is that, so how come we are able to formulate some of these regularities in the language of mathematics? Now, what Andre was saying with like Gelfand's talk and other people, so if there are patterns in nature, why is it that we have less of this mathematics in psychology, in biology, than we have in physics? You see, so to me, to think about this question as a question of metaphysics, like what is there, like what is there, or what kind of a world are we surrounded with, is one level. Another level, which to me is maybe like a starting point, is that why is there this particular relationship of math with some sciences currently and not others? You see, so because if the world is like full of these patterns that are supposed to be user-friendly to us, how come we don't have a, you know, I mean, I'm repeating myself, in like the sciences that are studying weather, and they're studying the climate, they're studying, you know, like why we have a more sophisticated mathematics. And that's one. And two is like there are a lot of mathematical concepts that like say infinity, I mean different levels of infinity, different cardinalities, etc. that like what do you want to make of those? Like are they also the results of a certain patterns in nature, or are they not? And then the question that I have for you is that what does abstract mean? You know, like how is it that we arrive at the abstract? Like is it just like we are creating it? Is it we are studying something? So to summarize it, it seems like the devil is in details when we are want to answer a question like that. And that's where we can learn a lot. But...
Yeah. I think the essential difference between physics and many other sciences in this respect is that in order to understand biology, you have to ultimately understand what goes on in individual cells. And there's chemical reactions there. And you need to understand chemistry. But to understand chemistry, you need to understand the quantum mechanics of these molecules, which is extremely complicated. And I suspect that when you get down to the bottom, you're a physicist again. This is why I'm a mathematician. You know, if I were doing biology, I'd soon be doing chemistry, and if I were doing that, I would soon be doing physics. And if I were a physicist, in fact, my father is a physicist, so I would soon be doing mathematics. That's the direction my mind naturally goes. So I would say that the inapplicability of mathematics in many of the other sciences is just because of the complexity of those other sciences. We haven't been able to see the pattern. I could go on. Let me just say quickly, abstract to me just means not detectable by our senses. So it contains a lot of things. And I want to leave it general. Abstract patterns should be almost anything. And yes, infinite cardinals are not doing much for science yet. In fact, if you look at my collected works, they're not doing much for science yet. So I don't claim that the abstract patterns that mathematicians study necessarily come from nature. They can also come from other areas of mathematics. They can also be made up on the spur of the moment. The last ones are not likely to be very good, but you know, there are geniuses who can do that. And yeah, it's abstract patterns for me. Math is abstract patterns, wherever they come from. And yeah, if some of them happen to fit physics, if some of them came from elsewhere, but then turned out to fit physics, we're very happy and write more grant proposals. And so my view is that mathematics is the business of abstractions. And if something else, physics, biology, whatever, can come up with things that can be abstracted, if there are patterns that can be studied systematically, that's a connection with mathematics. Okay, I should probably shut up. I see there are only 3 other hands
Yeah.
up.
Thank you, Andreas. I think in the interest of time, I see that we have a lot of questions. I'm gonna call on three more people to ask their questions. I'm gonna ask first Valeria, then Andre, and then Pseudo, and then we'll see where we go from there. So Valeria, you can unmute yourself.
Thank you. Thank you, Arezoo. That was lovely. Kind of very exciting to see what you've been working on and stuff. And, you know, because I also knew to want to carry on working on interesting stuff like that, I wondered why you didn't talk about the unreasonable effectiveness of mathematics in computer science, which is also a paper that exists from a few years back. And it's something that us in the Topos Institute are very interested in doing too, and thinking about that too. So I put in the chat for everyone what is the link to the paper. But my question is the fact that I think everyone that is discussing this so far, Wigner, the other, the guy of the distance, and everyone else, they're all discussing, assuming that we have this tight fit between modern theoretical physics and mathematics. And I think the problem with the guys from doing it for computer science is that we don't actually know if we do have a tight fitness or not. And I think what I want you to think about is not so much why there is an effectiveness or not of computer science, biology, chemistry, and neuroscience and stuff, but to actually kind of try to think a little bit about how do we discover if there is a tight fit or not? How do we measure this kind of fitness? That's the question. It's a hard one, I know. Don't expect you to kind of come up with an answer right away, but you could.
Yes, amazing. Give me a few months and invite me again. This is something I'm also fascinated by with like the applicability of math and computer science. It seems to me, see if that sounds right to you, that probably if we were to go to, say, 17th century and ask people, do you think that there is a tight fit between math and physics? They'd say, no, what are you talking? In the beginning, that like there is still debate about, okay, how should we think about like integral and about derivative, and like even the abstraction that was made about like how do we talk about masses, how do we talk about velocity, etc. It sounds like this is, when I'm talking about evolving relationship, is a sense in which it's not only in this kind of a romantic relationship, is not that only physics has come close to mathematics, but it seems they both have been like kind of getting closer to each other. So like right now that a lot of, say, mathematicians, some mathematicians are doing also computer science to realize like what are the needs of the field, and vice versa. It's almost like a relationship that is made through a lot of human work. It's not that, oh, we came up with the equations of motion all of a sudden, they were written in stone and they were correct, and now we realize. So part of my PhD work was on the use of complex numbers in quantum mechanics, which for Wigner and other people was so puzzling. But you look at years after years of people working on things really needing a certain thing that later was matrices, or later was they realized it has been developed in math, or complex numbers and so on. So a lot of work goes into creating these affinities, which affects both of fields. And then to me, it sounds like, but to expect a field that, like, say, let's think about calculus, for instance, or analysis, mathematical analysis, that has been developed in response to a particular problem, to expect that field of math to be useful in study of ecosystems, to me, this is a bit of a bias. But the openness to say, okay, let's look at what are the problems of these fields, and how can we come up with like tools that are effective in like multi-scale systems, as opposed to study of like a, time evolution of a local system, isolated system that we do in physics. So it's kind of like a very much involved human relationship. But that is all to say, I need to study more the current trends and come to your Monday lunches.
Yes, please do come. Yeah, we would love
you.
to have more discussions about that with you, Arezoo.
Thank you.
So Andre, would you like to unmute yourself and ask your question?
Yes. Thank you so much, Arezoo, for this talk. I very much agree with your analysis. I think you are quite right, kind of specifying actually the problem to, say, particular kind of physics. You also mentioned Wigner's view of mathematics, right? But actually, I tried to look a little bit in the context, and I thought it's probably not even, how say, just personal view of Wigner, right? Because the context is that that was the time in United States of this so-called new maths movement, then this kind of Bourbaki style textbook were promoted. And if I can just very short quote from Marshall Stone of 1961, in a short paper called Revolution in Mathematics, actually written in defense of this new maths. So he says, while several important changes have been taking place since 900 in our conception of mathematics or in our points of view concerning it, the one which truly involves a revolution in ideas is the discovery that mathematics is entirely independent of the physical world. And I think in that sense, probably Wigner really somehow follows the time. But my point is, and that's actually a question, that it's probably more than just philosophy, right? It's not philosophy in the sense that it's just some thoughts about what mathematics is, how it's related, and so forth. But it's also actually related to, say, what the Bourbaki people called architecture of mathematics, right? It's a particular way to rebuild the whole of mathematics, say, on set theoretic foundations. And then the question, say, is it probably the case that, what is your thought about that? That it's actually that kind of, say, architecture or that kind of foundation, right, which actually have behind this background, philosophical, that making mathematics quite independent of physics, is somehow responsible, on the one hand, we may say, for all this Wigner questioning, but also it's actually what just Valeria mentioned. And I made the same seminar, a talk, I think was 2 years ago, about Vladimir Voevodsky's ideas, because his concern was that kind of modern contemporary mathematics he himself was doing, like algebraic geometry, actually somehow lost this fit to physics. And he was very much concerned how, reconstruct it. So my question is, where do you think, for example, that like foundations of mathematics, like set theory is responsible? Or probably we should look elsewhere? Yeah.
Yeah, thank you, Andre. It's always
Thanks.
great seeing you. I see you in all the exciting places in the talks. And yeah, so there is a PhD dissertation, maybe like now it's turned into a book by Alma Steingart that is about where does this term even pure mathematics come from? Like it's this more maybe like the space between the wars or after Second World War. Everybody's like, yeah, physics helped with the atomic bomb and killed a bunch of people. We, on the other hand, we do pure things. We have, we are not involved in anything, like so mathematicians' way to say we are not responsible for the mess that, the result of other sciences is. But also like convincingly, she argues that along the lines of what you're saying, all of the efforts that were made, kind of a lot of messy years of the crisis in the foundations of mathematics, and then people tried to find different foundations and all the debates in different schools of philosophy of mathematics, which you know better than I do, they led to the importance of rigor, like placing rigor above even intuition, placing rigor and placing like, okay, and you need an axiomatic system, and then you need to be able to prove things on the basis of that. So the foundation there was set theory, but the feeling that people got was that now you can think about mathematics as separate from its primary origins safely, and it's kind of a building that stands on its own with the foundations that come from mathematics itself. Now, like if we want to talk about go those incompletenesses and we talk about like, okay, what are the problems with that? I mean, this is a different talk. But definitely, I mean, I think what is in the air around Wigner, and he doesn't study it further, he just adopts the spirit of his time, is a certain version of formalism. You're right, with the Bourbaki school, with like, and also just like Hilbert school with, so to me, that's where he gets most of his puzzle from. And now I look at structuralism, I look at like different schools that in philosophy of math that were developed since, and it seems like you can repeat the applicability problem. If you're a Platonist, you still have that problem. If you are a, structuralist, like still everybody has to tell a story about why do we have the particular, fit that we have. So, which to me sounds like the answer to what is mathematics has to be much more
Non, mais ça, c'est fini, il est fini.
and
C'était
multifaceted.
un zoom sur la...
Okay, I think I will try to mute. You can continue. Sorry, Arezoo. Arezoo, I think you can continue.
Yeah, that's it. I mean, I guess Andre and I, we agree on this. But
Thank you. Thank you for that question, Andre. And I think last we'll call on Pseudo. Pseudo, you can unmute yourself.
Can you hear me?
Pseudo? Yes,
Can you hear me?
we can hear you.
Great, thank you. First, thank you for a lovely talk, Arezoo. It's a fascinating topic. I'm glad you brought it to this context. I want to ask you about some distinctions which to me are the crux of the matter, and I'm curious whether it's something you've thought about much or can point us towards anyone who has. And it's about kind of not so much that why should math describe the natural world? I mean, that's, as Andreas pointed out, there are patterns, and so math is relevant, and it's a bare fact. Galileo, math is the language the universe is written in. That's there. And I feel almost that it's a tautology. But to me, the interesting question is kind of our relative access to the math and to the natural world. Like, I mean, the epicycles that you pointed out, and someone, Paul Taylor, pointed out in the chat, was a good example, because it's not that epicycles are wrong. It's just that it wasn't an unreasonably effective language. Like, you can describe all motions with any curve with a Fourier series, depending on how far out you're going to go, but it doesn't give you like a fundamental understanding of why something is, why planets move around the way they do. It just gives you a language for describing them. Whereas something like the example Wigner talks a lot about complex numbers and quantum mechanics, it's not a notation. It's that it's more work to do quantum mechanics without complex numbers than with it. And if you follow the hints, okay, if these are complex numbers, and let's look at their complex conjugates, let's look at Riemann surfaces, let's look at these other things. It turns out that those have physical meaning, or back even to the Kepler example, that it's not just that ODEs and central force laws are useful. It's that when you follow their detailed consequences, it turns out to be an incredibly accurate mirror of the system. And then you can keep going on, like Riemann geometry and general relativity, Lie groups and quantum field theory. So it's that things that we can have access to. Like, you can imagine some alternative where, we have some that all the mathematics that we can do is just not that useful for the world. Or like, I guess animals, they're doing something with quantity and causality, and they're doing something you might call mathematics, but nothing that they have access to is sort of getting them out significantly more than what they put in. And so it's this relative aspect to me that's amazing, that it's not just that you then describe the world with mathematics and then use this as a language, but then you now follow this to the ultimate consequences of what if this was a perfect description, and what things would be true of the natural world. And then the amazing thing is that so many of these things in great detail turn out to be true, or even when they're not true, sometimes they're useful to understand why they're not. It tells us to change the model. So this aspect, the relative aspect of our access to these things, is that something you can say anything about?
thank you. I probably need to hear more about it. So the question is about our access to certain structures. Tell me more.
Well, like,
what is the question?
Well, so I mean, it's not, to me, the question, it's not, the interesting question is not why should math describe the physical world. I feel like, if it's kind of, it's either tautological, or like if it didn't, then we wouldn't have gotten anywhere and we wouldn't exist and wouldn't be having this discussion, kind of, but rather that mathematics that we've gotten at, with just a few hundred years of, a few thousand people have worked just in the human scale, not a vast amount, things that are pretty low to the ground, turns out to be incredibly useful for understanding the solar system, understanding atomic nuclei, things like this, that a modest amount of mathematics has gotten us an incredible amount. Or like it's the beginning of Schrodinger's What is Life, where he reframes the question of why are atoms small in terms of why we're big, and he points out that that the individual atoms, obey statistical laws, and our ordered minds couldn't possibly be sensitive on that level of atoms. It's not that, why should there be these smaller objects, or at least from his point of view, but rather like, what about the nature of these laws enables us to discover them? Or in Feynman's lectures, he mentions an interesting point that I don't want to get far afield, but he points out, it gives a nice argument why classical mechanics could have been discovered first, because whatever scale it works at higher scales, whereas quantum mechanics does not have this property. So of course, classical was discovered first. So why is it that the mathematics we have access to seems to be disproportionately powerful? Like, if you look at human technological progress of the last few years versus the 50,000 years we've been more or less the species, it's all just spiked as a result of a few hundred years of mathematical advances.
Yeah, this is it's a fascinating question to which I do not have an answer. And it sounds like, I guess this is what a lot of people believe, that we have maybe spiked in the past few hundred years, or I am not sure. I'm not this is not my research, so I'm not sure if this statement is something I would agree on. So some people talk about even like humanity has lived for, I don't know, 3 million years, and it sounds like we just don't have access to all the amazing developments that they made. Well, we just think like they were running around being hunter-gatherers until like the agricultural revolution, and since then we've had a little bit of this mathematics, and recently we've had yeah, I'm not a historian but I doubt, my personal gut feeling is that I doubt it. I think like at any era, people feel like now we've got it, like we are the geniuses of the history, but I think like maybe at each developmental era, they've been fascinating results that they've had, some of which we have access to, some of which we don't. I don't know, help Andre, other people. So fascinating thoughts. I have no insight to share on that. Anyone has views on history of humanity?
It's not that I think that people were primitive earlier. I think we're primitive now. I think we're at the beginning of some exponential curve. But most of the big advances, whatever we did, I think were not mainly achieved through advances in mathematics. It wasn't that we figured out our agricultural strategies by sophisticated mathematics. We observed patterns for sure, and that's important. And no other animal did something like that. But it was kind of we observed the pattern, and then we just use that information immediately, rather than now put it into some category theoretical machine and looked at some differential equation and its singularities. We didn't like do these multi-step things that took us away from our original data, which is what we're doing now. That's, I think,
I don't know, Xiaowei. I think maybe this is kind of the kind of conversation that we should have after the streaming is closed.
Yeah, sure. I think that's a good idea. In the interest of time, I actually have one more question, which I will ask since I'm the host. Arezoo, I really love your talk, and especially your statement about there being a dance or interplay between math and physics. We have to understand the two-way street over there. And I think the same can be said about math and technology. And here at Topos, we talk about shaping technology for public benefit, or doing things ethically by using the math of connection and integration, which in our case, a lot of it is category theory. So based on your studies of this interplay between math and physics, do you have any advice for us, for those who are trying to shape technology? Do you have any advice on how we should be doing this right? For instance, like one of the things that we are very wary about is that we should not let the math tell us that reality is a certain way. We have to be careful about implicit biases in the math that we're using. And we should be careful to listen to the voices out there in whose lives are being affected by technology and incorporating that into the mathematics that we use. Do you have maybe advice of something like that for us, Arezoo?
This is really fascinating to hear that about your work. And recently, this has been one of my own interests, because I feel no matter how much we call what we do kind of abstract and we call it pure, we cannot close our eyes to the way that these things are used. And so I'm just going to tell you a bit of an anecdotal story. Like, I'm teaching philosophy, graduate seminar in philosophy of science, and I'm inviting speakers from all around the world to join us via Zoom. The kind of my pet peeve, the question I ask them, I say, okay, if this debate is settled one way or the other, like I'm teaching unrealism, anti-realism in philosophy of science, what is the effect of it in the outside world? Which is a question that I was asking as a grad student, and everybody was like, this is philosophy. So I really want to know, and I think given the ecological crisis we are in, and all the issues we are dealing with as on this planet at the moment, it's very kind of, to me, unreasonable and irresponsible to continue doing the work we were doing, because it's just intellectually so fascinating. I'm losing sleep myself over what is like all these amazing things that I've learned, and I've sharpened the tool of my mind with getting a PhD, etc. Like, what is it at the service of? So to me, I really congratulate all of you guys for taking this seriously, because I think we can't afford hiding behind the fact that we do mathematics or we do philosophy, and good luck finding or applying it in the world. We are not responsible for that. To be thinking about these questions is an amazing step, and to forgetting about, like, also to forget that there is no such thing as a pure field. We got to take responsibility for where the tools that we developed are being used. I don't have an advice, but I would love to join your efforts in making what we are doing really useful and really applicable. So I shift my own philosophy of science courses toward like maybe a shift of a view from like the super emphasis on physics to things like that have to do, maybe like we need a different paradigm that place us as part of the ecosystem, what sometimes people call mathematics or philosophy of interconnectedness. What would it be like to take seriously our role in the destruction and also maybe restoration of the planet? What would it be like to take our role seriously with underrepresented groups, with like the wars that are happening everywhere? So you see, I think like the first step for us is to kind of wake up from our abstract dreams and realize we have responsibilities to. So I'm also talking with my colleagues in different institutes that are developing AI, and I say, well, as a philosopher, I would love to be part of what you're doing, because we can't afford closing our eyes to how technology is developing and how it's going to affect people in the future. So
yeah, that was beautifully said. I think, yeah, you're right, that the first step is for us to wake up and to understand that the tools that we're using does have an effect on the world. We cannot just sit back and assume that because we're doing pure math, it has no influence on the world. But instead, actually, the math that we do does have great power in changing and affecting the world, and we have to take responsibility for that.
yes.
And I think that is probably the most important first step. And in fact, I really liked your talk, because I feel like a lot of the points that you made about math and physics directly apply to technology as well, and just be able to think about through that context really helped. So thanks again. So let us all thank Arezoo again. This has been a really wonderful session, and thank you for addressing our questions as well, difficult as they are. Thank you so much for your insightful replies. And I'm going to end the live stream now.
Thank you, all of you.
Yeah, thank you.
It's been a pleasure.
Yeah, very, very nice. Thank you so much. But I really must go now, so I'll kind of send you email later on, okay? Thanks a
Thank you
lot.
so much, Valeria. It was lovely seeing you, all of you.
Lovely
Thanks
seeing you
for
too.
the inspiration.
Thank you. Bye.
Okay. Okay. Thank you. Thank you very much.
Thanks a lot.
And
Take
then,
care.
Take care. Bye.
Yeah, thanks everyone. I'm still trying to end the live stream, but please feel free to. I'm having some technical difficulty here. Just give me a moment. Okay, I am having a problem with ending the live stream, but I think if there are no other questions, thank you, Arezoo. It's
Please
been
feel free to
wonderful.
write to me. Thank you so much, Andra.
Yes,
Thank you,
I
Sudhi.
will write to you, and
Thank
we hope to have you over at Topos for more discussions.
Looking
Since we are
forward to
nearby,
that.
we should totally do that. And yeah, thanks everyone for attending today's colloquium, and the next one will be on December 5th. So we'll see you then. Thanks.
Thank you. Bye.
Bye-bye.
Okay. Goodbye.